Now, the idea of induction is not only to prove the series types, we can prove other things with induction as well. So have a look at this one. We're going to prove that n times n plus 1 times n plus 2 is always divisible by 3. If you think about it logically, it has to be true. Because if you get 3 consecutive numbers, one of those consecutive numbers must be a multiple of 3. It's impossible to pick 3 numbers in a row and one of them not be a multiple of 3. So we're going to use the same idea. We'll prove it true for the very first case. So if I grab the first 3 consecutive integers, I'll get 1 times 2 times 3, which is 6. And yes, as we all know, 6 is divisible by 3. So, okay, that's certainly true. The question now is, what is going to be my assumption? My assumption is it's going to be true for where n equals k. So I could pick any 3 consecutive integers. Now how do I write that down? The way I write it down is like so. I'm going to say, well, the number I'm going to pick, 3 consecutive integers, so k plus 1, k plus 2, is divisible by 3. Well, as an equation, I could write that as equals 3 times something. I've called it p, where p is a whole number. If that's 3 times a whole number, it's divisible by 3. I'm going to now prove for the next case, if I would grab the next grouping, k plus 1, k plus 2, k plus 3, I want to show that's equal to 3 times some whole number. Now, it's not going to be 3p, because the answer is going to be different, so I'll call it q. Q some whole number. You can feel free to pick any letter you like. You can be as creative as you wish. But just as a tip, don't pick a letter you've already used. That's where it can confuse things. I've got k plus 1, k plus 2, k plus 3. I notice in my assumption that I have k plus 1, k plus 2. It was k plus 1, k plus 2. I've got to get my assumption in there somehow. So if I rewrite this as k times k plus 1, k plus 2, there's my assumption. But then it would be plus 3 lots of k plus 1, k plus 2. So essentially, I've just expanded out the last parentheses. But that allows me to substitute in for my assumption. Because that, I said, was 3p. And now have a look. I've got 3 times p, but I've also got 3 times k plus 1 times k plus 2. We have a common factor of 3. So I can factorise out the 3, and it's true so long as p plus k plus 1, k plus 2 is a whole number. We know it is a whole number because we said k was a whole number. So therefore k plus 1 is and k plus 2 is. And if I multiply whole numbers together, I'll get a whole number. I'm going to add it to p, and we said that was a whole number. So yeah, q will always be a whole number. So there's my proof. It's true for k plus 1 if it's also true for k. And then we can say, well, look, yep, we worked it out, it was true for 1, so hence it's going to be true for all the others. Let's try another one. 3 to the power of 3n plus 2 to the power of n plus 2 is divisible by 5. So this one's not as immediately obvious as the last one. Okay. Well, let's see what happens when n is 1. When n is 1, I get 3 cubed plus 2 cubed ends up being 35. So yep, works for that one. 35 is divisible by 5. Good. My assumption, okay, well, 3 to the power of 3k plus 2 to the power of k plus 2 will equal 5 times something. Again, I'll call it p. We want to prove for the next case, so it's going to be 3 lots of k plus 1, 3k plus 3, and then it's k plus 1 plus 2, k plus 3. We want to prove that's 5 times something. 3 lots of 3 to the power of k plus 3 plus 2 lots of k plus 3. My assumption, 3 to the power of 3k, was it plus 2 to the power of k plus 2? So it's equal, 5p, not 3p. How do I get that in there? And this is one where maybe it's not immediately obvious, but what I can do is I can rearrange my assumption. See, this 3 to the power of 3k plus 3, I could rewrite as 3 to the power of 3k times 27. And then if I think of my assumption as 3 to the power of 3k equals 5p minus 2 to the power of k plus 2. So just rearrange the assumption. And then I can substitute in for that 3 to the power of 3k. Could have done a similar thing with the 2 to the power of k plus 2. I could have rewritten 2 to the power of k plus 3 as 2 times 2 to the power of k plus 2, and then rearrange the assumption to make 2 to the power of k plus 2 the subject. It should work either way. Alright, it's still not immediately obvious that that's a multiple of 5. So let's expand out. I've got 135p minus 27 lots of 2 to the power of k plus 2 plus 2 to the power of k plus 3. But, as I said just before, 2 to the power of k plus 3, I could rewrite that as 2 lots of 2 to the power of k plus 2. So negative 27 lots plus 2 lots gives me negative 25 lots, and that's divisible by 5. I can now factorise 5. So 5 outside of 27p minus 5 lots of 2 to the power of k plus 2. It works so long as that is an integer, and again it should be, because we defined everything. K was an integer, so 2 to the power of some integer should be an integer. P was an integer, so yep, that should work. 27p minus 5 times 2 to the power of k plus 2 should be an integer. And then, hence it's true for k plus 1 if it's true for k. And since we tested it for 1, we can now induce that it's true for all of them. So a few more out of the same exercise. Those ones are more on this divisibility idea.